So the last concept in chapter 2 that I want to talk about is normally introduced a little bit later in the course, but this textbook we're using is introducing it now, and I'll discuss it. I'm trying to stick to the book as closely as I can, and it has to do with quantifying molecules and atoms in chemical reactions. So in the lab, we have to have a way to measure the mass or a way to count atoms and molecules, and this is the mole concept. And we'll talk a lot more about the mole and how we use that in more detail. I think in chapter, I think it's chapter 6, but I'm not 6 and 7. But for now, just understand that this new word, the mole, it's tells us the amount of something. It's like a dozen or a pair or a gross, words we use to indicate the amount of something. It's defined as the amount of a substance that contains the same number of discrete entities, could be atoms, molecules, or ions, as the number of atoms in a sample of pure carbon-12. They chose carbon-12 as the standard. So the isotope carbon-12 with 6 protons, 6 neutrons, and 6 electrons, they just said is 12.000 out to infinity grams. It's exactly 12 grams. And they based all the other elements in the periodic table on that standard. The mole provides a link between the mass of a sample and the number of atoms or molecules. So a mole is don't be afraid of this concept. It's not anything that difficult to understand if you just keep this in mind. We all understand when I say a dozen that it means 12. We all understand when I say the word pair, it's 2. So all I'm saying is that when I say the word mole, I just mean a very large number of something. And it turns out to be Avogadro's number, 6.022 times 10 to the 23rd something per mole. And if you write that out, it's actually a huge number. It's, if you had this many, for instance, peas, I believe, or some small spherical object. If you had this many, it would actually cover the entire surface of the Earth to a depth of many miles. So it's an incredibly, almost incomprehensibly large number. So we don't obviously want to write it like that. We want to write it in scientific notation. So we usually round it to 6.02 or 6.022 times 10 to the 23rd. And that's that famous number, Avogadro's number. The key point is that the masses of 1 mole of elements are different. So, but all you're doing when you look in the periodic table at the atomic masses of elements is that you're looking at Avogadro's number of atoms or molecules. It doesn't matter what you're talking about. It's just a way of counting them. So if you look at a periodic table, the numbers here, I know it might be kind of hard to see, but this is figure 225. If you have 65.4 grams of zinc, you have a mole. If you have 12 grams of carbon, you have a mole. If you have 24.3 grams of magnesium, you have a mole, and so forth. These numbers here are just the atomic masses of the elements that you read directly from the periodic table. Now, the periodic table that you might be looking at would generally have 2 decimal places in it and not just 1. If I can find a periodic table while I'm talking to you here, I'll bring one out here. But again, that's all these numbers mean. And that's a very important thing to realize, is that when you have the atomic mass of an element, you're just simply stating that you have Avogadro's number of those atoms. So we have a special way to express the masses of atoms and compounds. Sorry, that was out of view. We call it the molar mass. You might hear somebody call it the molecular weight, or they might call it the formula weight or the formula mass. But a molar mass is the most accurate term to use. The molar mass of an element or compound is the mass in grams of 1 mole of a substance. And I'll give you some examples. And it's a property expressed in units of grams per mole. So earlier on in the chapter, recall that we were talking about the masses of elements in atomic mass units. which is a very tiny unit. We can't actually weigh atomic mass units in a lab. We have to weigh things in grams. So because of the way we define the atomic mass unit based on carbon-12, atomic mass units in grams essentially have the same meaning. So the key point is that the molar mass of any substance is numerically equal to its atomic or formula mass in atomic mass units. So carbon-12 atom weighs exactly 12.000, etc. A mole of carbon-12 atoms has a mass of 12.0. Now we can think of the unit grams. And that's where the molar mass comes from. We would say that carbon-12, or a mole of carbon-12 atoms has a molar mass of 12.0 grams per mole. We have to put that per mole, which we write sometimes as G/mol for short. That means molar mass. So each of these samples in this picture contains Avogadro's number of molecules or formula units, 1 mole. Here we have 130.2 grams of octanol. It's just a clear colorless liquid. This red powder is mercury iodide, HgI2. It's a very heavy molecule because mercury is a very heavy element. So it takes 454.9 grams of that element to make Avogadro's number. 32.0 grams of methanol is a mole, and so on. But all these things have, what all these compounds have in common is they contain the same exact number of molecules or formula units. They all have 1 mole in them. But I'll say this again, the reason why they have different masses is because even though they have the same number of particles in them, each particle or atom has a different mass. That's the periodic table. So therefore, if you add all those up, you get different masses. So the average atomic mass of a carbon atom, if you look on the table, is 12.01. That means the molar mass is 12.01 grams per mole, but it has this many Avogadro's number atoms per mole. Goes for any element. Hydrogen's average atomic mass is 1.008. We will sometimes round that to 1.01. But it also means that for a mole of hydrogen atoms, it would have a mass of 1.008 grams. Oxygen's atomic weight is 16.00. Its molar mass is 16.00 grams per mole. Don't confuse molar with molecule. Molar just means per mole. Sodium is 23.0 AMU, but a mole of sodium atoms is 23.0 grams, and so forth. I think you get the picture. Chlorine is 35.45. So I would like you to use the atomic masses with 2 decimal places. Atoms are very tiny. Consider how large the Atlantic Ocean is. So even though you have a tremendously large number of atoms in these samples, their masses are they're appropriate for a lab. We can actually hold these amounts in our hands. But to give you an idea of how small atoms are, if you think of the Atlantic Ocean, it's huge. In a single teaspoon, which is about 1 milliliter of water, in a single teaspoon of water, there are a tremendous number of atoms. There are about 3 times as many atoms. I should have probably written this out earlier, sorry. As there are teaspoons of water in the ocean. In the ocean. I'm running out of room here. So that's a pretty amazing statement. In a single teaspoon of water, there are about 3 times as many atoms as there are teaspoons of water in the ocean. Imagine you could actually empty the ocean with teaspoons and count them. If you did that, you still wouldn't have as many atoms as there are in 1 single teaspoon of the water when you break it down into hydrogen and oxygen. The relationship between formula mass, the mole, and Avogadro's number can be applied. We can compute various quantities that describe the composition of substances. So this is where unit conversion comes in. This is how we're going to use this concept of grams per mole. If you have 4.7 grams of potassium, for instance, we might ask you, how many moles is that? Well, if you look in a periodic table, you would see that the atomic mass of potassium is 39.1. I'll just use one decimal place for the examples. So 1 mole of potassium, this is right out of your book anyway, 39.1 grams. We write it like that. So this is this is how you're going to apply this molar mass. You're either going to have it the atomic mass on top, or the molar mass on top, or on the bottom. In this case, we have it on the bottom because we're trying to convert grams of potassium to moles. So you just simply divide by the atomic mass and you get 0.12 moles of potassium. That's a pretty routine calculation that you'll do a lot when we talk about this again in chapters 6 and 7. And there's another example that your book does. I won't do all of these, I'll leave that to you. We might ask you how many copper atoms are in an old penny that's 100% pure copper. Now, how would you do that? Well, you'd be given this information. You would be given the fact that a copper penny weighs about 3.11 grams of copper. That's an older penny. Newer pennies might weigh slightly less than that because they have zinc in them. But let's say it weighed 3.11 grams of copper. How could you calculate how many atoms of copper there are? Well, the only link between numbers of atoms and amount is Avogadro's number. So first convert grams of copper to moles. So you'd write 1 mole of copper. We abbreviate the word mole, M-O-L, little lowercase m. And look in a periodic table, you'd see that the molar mass, or atomic mass of copper, is 63.55 grams for every mole. And you see grams on top cancel with grams on the bottom. And there's only one more step to convert that to numbers of atoms. We use Avogadro's number. There are 6.022 times 10 to the 23rd atoms of copper. You can just write atoms in 1 mole of copper. And you can see that unit's on the bottom, that unit's on the top. And if you crunch the numbers, you would get to 3 sig figs, because this measurement has 3 sig figs. We should round our answer to 3 sig figs, so we'd get 2.95 times 10 to the 22nd atoms. So you would expect a very, very large number. So again, one strategy you should follow is the fact that you should give a ballpark estimate. So 3 grams of copper, to me, since I've been doing this so long, I realize is about 1/20th the mass of 1 mole. So my answer should be about 1/20th the number of 1/20th Avogadro's number, which this is. It's a power of 10 less. I'll do this one more. I'll leave this last one to you guys. It's in the book, you can just look, but the technique for solving this problem where you're trying to figure out how many carbon atoms are in a molecule of saccharin, which is an artificial sweetener, is done in exactly the same way as this. I don't like that pen, I'm going to try a blue one. How many water molecules are present in a single drop of water? But now we give you the volume. So what you would do there is you have to add an additional step. You have to use the density of water. Let's just assume the density of water is 1. For our purposes, that's usually good enough. So to convert milliliters to grams, you multiply by the density. So milliliters on top cancels with milliliters on the bottom. So 0.1 milliliters of water is 0.1 grams. Now we convert grams to moles by doing the same thing as we did up here. We multiply, or we actually divide by the molar mass of water, which is 18.02 grams. How did I get that number? I just simply looked in a periodic table and I added up the mass of 1 hydrogen, which is 1.008, actually 2 hydrogens, so 2 times this number plus this number, you can see is just a little bit over 18.02, but I want you to use those 2 decimal places. And then one more step, use Avogadro's number, 6.022 times 10 to the 23rd molecules are present in a mole. And we can use this for ions as well. And that, if you round to 1 sig fig, is about 3 times 10 to the 21st molecules. It's important, especially when you're a beginner, to write numbers of what. Don't just leave this number without a unit. In this case, it was copper atoms. You can write atoms as sufficient. or we're talking about molecules. If I asked how many atoms there are total, I can do that pretty easily. Let me just do one more step to show you how the ratios work. So if I asked you convert that number of molecules of water to atoms, all you'd have to do would be add one more step. So 3 times 10 to the 21st molecules. And you should write out molecules of what so you can keep track. You'd write one more conversion unit, a true statement. Remember, these are just true statements. A water molecule is HOH, like this, H2O. So there's 3 atoms in a water molecule. So you'd write, there are 3 atoms in one molecule of water. That's a conversion unit that you just made up by looking at the structure. But molecules on top cancel with molecules in the bottom. All you're doing now is multiplying your initial answer by 3, and you get 9 times 10 to the 21st atoms total. And that makes sense. If you just took this many of these and broke it up into pieces, you'd have 3 times that. 1, 2, 3, and there you go. I just proved it to you. So I hope that is not too difficult for you. You should practice doing some homework problems. You can look on page 101 to get the solution to this problem, but it's done exactly the same way as the ones I've just shown you here.